We're generally interested in the effect that temperature might have on the rates of a reaction, just as we were interested in the effect that temperature had on various thermodynamic potentials like Gibbs energy and enthalpy. So how can we get to the heart of that? Well, we know that our rate laws depend on they're generally of the form, they depend upon a rate constant and the concentrations of various reactants raised to different powers. I'll just leave it as a second order reaction written here. But I'll point out that these two quantities, these concentrations of these reactants, really don't depend upon temperature. So the only place that we can go to find an effect on temperature is the rate constant itself. Now, what does happen to the rate of a reaction as we change the temperature? Let's take a look at some possibilities. Well, I think first, the general effect that temperature has on the rate of reaction is to increase it, and it tends to increase in a curve that looks something like that. I mean, obviously not exact, but you get the general idea. So we're just plotting the rate of the reaction here, not the rate constant. All right, this is not the only way that reaction rates change with temperature, however. Depending upon the mechanism of a reaction, the temperature dependence can be very different. For example, if you have a catalyzed reaction that's mediated by a catalyst that may be turned off and on as you change the temperature, that could result in a very different sort of profile for the temperature. But this is the one that I'll say corresponds to most of the reactions that we'll be interested in, so this is the one we'll focus on. So what are the effects of temperature? What can we basically lay these down in terms of their effects on different things that we know lead to chemical reactions? Well, first of all, we can imagine that temperature would affect the frequency with which collisions occur. We've already seen some mathematical representations of how often molecules collide, and that had a temperature dependence associated with it. Now, it also will affect, though, the fraction of the collisions, and I'll say with sufficient energy. Now, we will have to specify what we mean by sufficient energy, but we want to activate a reaction, and oftentimes that means breaking some bonds or rearranging some things, and all of those events cost energy. So the collision itself or the conditions of the reaction have to provide enough energy for that to happen. Now, I'm going to start by talking about a sort of a sort of empirical way of writing this down, and then we'll get into more details about exactly how the temperature can affect the reaction rate. All right, the empirical evidence that I want to present first is that from various experiments, mostly done in the 19th century and maybe in the early 20th century, suggested that one could relate the rate constant, this is the logarithm of the rate constant, taking derivative with respect to temperature, to a constant divided by RT squared. And this constant here had units of energy, but otherwise wasn't given any other special meaning. Well, we've since sort of made an association of this energy that appears in this equation with something called the activation energy. And for a wide variety of reactions, this relationship between the rate constant as a function of temperature and this activation energy divided by RT squared leads to a fairly constant value for the activation energy. So this appears to be a good empirical relationship to follow up on. Now, before I get into talking about this more, I want to make an observation, and I hope that this is the kind of thing that you get out of this course. But when you look at an equation like this, does it look like another equation that you might have seen? And the one I'm thinking of is, remember, the Gibbs-Helmholtz equation. Now, this had to do with very different sort of circumstances and regarded different types of processes, but the Gibbs-Helmholtz equation basically said that the partial derivative of G over T with respect to temperature, and this is all at constant pressure, was equal to minus H over T squared. Okay, so what I want to do is compare these two. Okay, now granted, the Gibbs energy is an energy quantity and the rate constant is not an energy quantity. But there appears to be some kind of, if you will, some kind of relationship that we might draw between the Gibbs energy over temperature and log of this rate constant. In fact, I'll go a step farther and say that this minus sign can go over on the left-hand side. So it's really a relationship between minus g over t and the rate constant. Similarly, we might draw a relationship between the enthalpy that's appearing in the Gibbs-Helmholtz equation and this activation energy. Now, what I'm doing is I'm simply trying to suggest that when we have mathematical equations with a very similar form, that there are some things that we can learn from that similarity. As it turns out in this particular case, though, as we'll see probably in the last video, there's more to this relationship than just a coincidence. And I'll leave it at that, but I'll simply entice you by saying that we can, in some ways, relate the rate constant to a Gibbs energy change, though perhaps not the one you're thinking of, and that this relationship between these quantities is actually more real than imagined. All right, so one of the simplest ways that we can take an expression like this, empirical expression, and get some meaning from it is to actually integrate it. So let's do that. So what I want to do is I want to rearrange the equation a little bit. So it'll say log of k is equal to e over r, and then I'll go ahead and make that e sub a dt over t squared. Now this represents something. I've got all the temperature is on the right-hand side, so I can integrate these equations to get, hopefully a relationship that has some meaning. Well, when and I should have left this as a d log k. Sorry about that. So if I integrate d log k, I'm just going to get log of k. And if I integrate this equation, these I will take to be constant, and I integrate 1 over t squared. That's just going to give me negative 1 over t, so I'll have negative ea over rt. All right, so this is an interesting relationship between k and temperature, but I also want to note that we haven't put limits on these integrals, so I'm going to have also an integration constant, and I'm going to express that integration constant as log of some number a, and we'll talk about a in just a moment. All right, now this would be one way to write down the result of this, but if we solve for k, and I'll now explicitly write k as a function of temperature, what I would get is an expression that looks something like this. And this is an equation that you might recognize. This is something called the Arrhenius Equation, and it basically tells us how the rate constant k depends upon temperature. And in fact, it accounts for a very strong temperature dependence for most rate constants. In fact, you don't have to change the temperature very much to see a very different rate constant. So most reactions are enhanced greatly by changing the temperature, by increasing the temperature as we go. Now, how would we use this Arrhenius equation to understand more about k of t? Well, first of all, there are two parameters in this. Okay, there is EA, which we've already talked about, is the activation energy. So it is, in a sense, the energy that is needed to activate the reaction. And then there is this integration constant. Now, it's not quite so innocent as an integration constant, but it's sometimes called the frequency factor. And it's related to the collision frequency. So there is something to this. Okay, now, we mentioned up here that the effects of temperature were to change the collision frequency and to change the fraction of collisions with sufficient energy to activate the thing. Well, this one accounts for that second point, the activation energy. We would now have enough energy to activate the reaction. The frequency factor, though, has a hand in the first one, the collision frequency. So what we'll find is that, in fact, this constant that came out of the integration more properly can be thought of as a temperature-dependent constant. Well, so it wouldn't be a constant, would it? All right. This formulation that led to the Arrhenius equation. I should probably write that down for you. This formulation was based on an empirical observation for a series of reactions for which A is relatively constant. This temperature dependence of A is actually a fairly weak temperature dependence, and it's not nearly as strong as the exponential temperature dependence that we see up here. Okay, but it will nevertheless play a role in the temperature dependence of our rate constant. Now, how would we relate these things somehow to a reaction diagram? So if we had a reaction energy diagram, and we've drawn these a lot, and we've even labeled the things that we're interested in, okay, but an exothermic reaction might look something like this, and what we would be interested in is drawing a line across here and then the height of this barrier, and the height of that barrier is something that we associate with this activation energy. So the thing that really controls the rate of reaction is how high is that barrier that the molecules must traverse in order to get from reactants on this side to products on this side. All right, so this is the thing that really controls the rate of that reaction. All right, I want to say a last few things about the frequency factor, A of t. And I'll simply note that it controls the collision frequency, so that's where that effect comes from, that was noted up here. It also can incorporate the steric effect, which we've referred to as the orientation of the collision. Now this one is a little bit trickier to capture, but nevertheless all of these kinds of things are captured in this constant here. Now how would we find the value of these constants? Well, here we have a prescription right here for doing that. It tells us that if we plot log of k versus 1 over t, what will we get? Well, we'll get a series of points, moderated of course by experimental random fluctuations, but we'll get a set of points that lie on a line, and in that line the slope of the line would be equal to minus the activation energy over r. So this is how we would actually measure the activation energy for a given reaction. So what we have here actually with the Arrhenius equation is a really slick way to measure an energy that we otherwise would have great difficulty measuring. Normally we can measure, for example, the difference in the energies of the reactants and the products, and that's just delta H for the reaction. Okay, that's easy to measure because we have stable molecules here and we have stable molecules here, and we can generate various ways of measuring that. But whenever we have an endpoint that isn't stable, like the top of a barrier, that's when we have some more difficulty. So this equation, this ability to measure the activation energy by measuring the rate constant at several different temperatures, is a very powerful technique, and one that you'll get a little bit of practice on in a couple of problems.